In this video, we are going to talk power in circuits with an AC source. The basic definition of power is the product of the current and the voltage. We generalize this and add a phase difference between the current and the voltage. We then write as shown. We then use the trigonometric relation shown and define phi as the difference between phi I and phi V. We then obtain a new equation as shown. This power is not possible to measure with a simple multimeter. If we then solve for the average power, the second term with the time component vanishes, since the average of cosine over time for all time is 0. We are then left with the expression for the average power to be equal to I naught V naught over 2 times cosine of phi. In a purely resistive circuit, the average power is then equal to the top equation, since there's no phase difference between the voltage across and currents through the resistor. In a purely capacitive or inductive circuit, there is no average power. Thus, both the capacitor and inductor do not consume or dissipate any real or true power. Taking a look at the graph, where both the voltage and the current are in phase, power is always used up, and there is no power returning to the resistor. However, the inductor and capacitor do dissipate an imaginary power, and we'll understand this a bit better in a little while. First, let's take a look at the second term in this equation. This is an equation which we derived earlier. In an inductor, the phase difference between the voltage and the current is positive 90 degrees. Thus, if we set phi I to be 0, phi V should be 90 degrees. First term vanishes because phi I minus phi V is 90 and cosine 90 is 0, while the second term becomes as shown. Taking the average power of this, we obtain the expression as shown. What does this power mean? If we take a look at the figure, we see that the voltage and current waveforms are out of phase by 90 degrees and the voltage leads the current. If we multiply these two results, we have the shaded waveform for the instantaneous power. Notice that between the angles 0 and 90 degrees and 180 and 270 degrees, the power is negative, while between the angles 90 and 180 degrees and 270 and 360 degrees, the power is positive. Thus, you can see that the power is being used up and then returned alternately. Thus, power is moved back and forth through the inductor, and therefore it's not really used up. In one full cycle, the total power used up is just 0. The magnitude 1/2 I naught V naught is just the average of the absolute value of the power. This is the amount of power that is being exchanged. If we consider capacitive power then, the phase difference is negative 90 degrees between the voltage and the current, with the voltage lagging as shown in the figure. Then we obtain the following expression as shown. The negative sign only indicates that the orientation of the sine function. Again, the power alternates between consumption between 0 and 90 degrees and 180 and 270 degrees, and replenishment between 90 and 180 degrees and 270 and 360 degrees. There is no power that is used up, but only power that is exchanged back and forth in the capacitor. In one full cycle, the total power used up is just 0. The magnitude 1/2 I naught V naught is just the average of the absolute value of the power. This is the amount of power that is being exchanged. We can now summarize power in AC circuits. For real power, we have the following expression. For reactive power in a pure inductor, we also have the following expression. For reactive power in a pure capacitor, we again have the following expression. Typically, the real power has units of watts, and the reactive powers has units of volt amperes. There's one more type of power called the apparent power, which combines both the real and reactive powers. The equation is shown. We can draw a power triangle for the AC circuit. The ratio of the real power to the apparent power is called the power factor. As you can see, the power factor can be anywhere between 0 and 1. If the power factor is 0, then there is no real component, and the AC circuit is either capacitive or inductive, depending on which power component is larger. If the power factor is 1, then there are no imaginary components of power, and the power is solely due to the resistor consumption. If the power factor has a value between 0 and 1, then if it is more inductive, the power factor is said to be lagging, since the real power lags the reactive power. Otherwise, if it is more capacitive, then the power factor is said to be leading, since the real power leads the reactive power. I hope you've understood the lessons in this video. You can always take a note of anything that might confuse you or need clarifications from, so that we can discuss them in our regular consultation sessions. Our next lesson involves further analysis of RLC circuits and their applications.